just starting off with some matrix multiplication stuff. Though I have ulterior motives here. First of all, just as a reminder, anytime I'm multiplying things, checking the dimensions is a good idea because that's what's going to let me know if I really can multiply these. So this is a 2 by 2 times a 2 by 1. Again, rows before columns. And since my inside dimensions match, we can do the multiplication, and my outside dimensions tell me how big the answer is going to be. So I know my answer will be a 2 by 1. So if I do this multiplication, I'm looking at 4 times 2 plus -2 times 1, so -2. And then I've got -3 times 2 plus 9 times 1, which is a 9. And if I simplify those, I think I get 6, 3. Does that look right? Cool. Second one, same dimensions, so I don't have to worry about the dimensions matching. I know my multiplication is going to work. So I've got 4 times 1 plus -2 times -1, so that's a +2. -3 times 1, so that's -3. And 9 times -1 is -9. So here I am looking at 6, -12. Feel like what other people got too? Okay. So this first one, I claim something kind of special happened, but I want to talk about the second one first. In a purely mathy context, right? I'm not going to try to connect this to biology yet, but in a purely mathy context, I've got a matrix and some vector, and multiplying a vector by a matrix is called a linear transformation. I am transforming this vector into this other vector. Graphically, I want to look at this second one and see what happened. So I started off with the vector 1, -1, and I'm going to go ahead and anchor that at the origin. Although my vectors don't have to be anchored at the origin, it's just going to be easier for me to show what's going on. So if I anchor this at the origin, this says 1 to the right and down 1. So 1 to the right, down 1, and I'm going to make it pretty small because I realized to let my other numbers get real big. So that's the vector we started with. And after this transformation, this is the vector we ended up with. So this vector got sent to like a new place. It got sent to this thing that's 1, 2, 3, 4, 5, 6 to the right and down 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Woo, okay. All the way down here. So this vector changed the magnitude and also the direction. And in general, when I multiply a matrix times a vector, I'm going to change both the magnitude and the direction. But sometimes a really special thing happens. So this was what happened for number 2. Sometimes a special thing happens, and I want to take a look at what happened for number 1 over here. So we started off with the vector 2, 1, 2 to the right, up 1. And I ended up with the vector 6, 3. 6 to the right, up 3. And in this transformation, my vector changed length but kept the same direction. And when that happens, we call this special vector an eigenvector. If anyone studied German in high school, that eigen root word meaning only or one. And so it's the one special vector. And I can find that out from graphing it, but I can also see it just in terms of the equation. So changing magnitude means the vector I started with has just been magnified or shrunk or flipped to be negative, but I can write this 6, 3 vector really as saying 3 times that original vector of 2, 1. And that number that scaled the vector, we give it a special name too. And that number gets the name eigenvalue. Now, if we tie this kind of back around to the biology, and I think about this as an iterative process, or like I put one vector in and I got one vector out, and I'm thinking about that over time. If I put in some X and Y values, and the way they changed for the next time was that I just multiplied them by a number, this actually matches what happens when we're thinking about exponential growth. So we're going to pair those two things up in 17C. And for right now, we're going to practice finding these eigenvectors and eigenvalues, because really these are going to help us to find stable age distributions, where if we start with that particular age distribution, then that ratio of parents to offspring will stay constant over time. They'll be increasing their population, but the ratio of parents to offspring will stay the same. Class on Tuesday, by hopefully making a big deal about the fact that the interesting stuff happens when we try to divide by 0. And so I'm going to bring that all back together. What it's going to look like if I have found my magical eigenvalue eigenvector pair is that my matrix times that eigenvector would be equal to the eigenvalue times the eigenvector. So lambda is usually the letter that we use for the eigenvalue. And I think it's secretly the reason that our textbook writes the exponential growth equation as y equals, oh, they don't use c. Okay, they use y naught e to the negative lambda t, because there is a connection. This is just like, we're not going to talk about this right now, but just know it's hiding in the background. It's going to come back out in 17C, might come out next week if he lectures Wednesday. Otherwise, probably 17C. So this is like our fundamental equation for what it means to be an eigenvector eigenvalue pair, that multiplying a matrix by this vector is equivalent to multiplying the vector by a number. Now comes the fun part. I'm going to solve this equation, and I'm solving this equation by moving everything to the left-hand side. So I'm going to have a times x minus lambda times x is equal to 0. And then I'm going to do what I generally do when I'm trying to solve something. I'm going to factor it out. There is a thing we have to be careful about factoring here, because matrix multiplication is not commutative. It matters which thing is on the right and which thing is on the left. So when I factor this, I'm actually going to factor the x out to the right. because it's on the right-hand side of the matrix. Now I've got another problem. Lambda, we already pointed out, is a scalar. My A is a matrix, and I can't take a matrix and subtract a number. So the trick for this is that we're going to insert a 1. Multiplying by 1 doesn't change the problem, but the 1 we're going to insert is our matrix version of 1, meaning we're going to insert the identity matrix. So I'm actually going to come up to the previous step, and I'm going to insert an identity matrix for myself, which means that when I factor out, I'm right here. Okay, I've got two things that are multiplied to be 0. One of those two things has to be 0, right? Well, if this is 0, all the critters are dead. That is not the interesting solution. Our interesting solutions actually happen when this equation can't be solved by finding an inverse. So I'm going to pause for a second, and I'm going to call all of this thing over here some new matrix B. So if I think about an equation that looks like matrix B times X is equal to 0, for sure this works if X is equal to 0, but that's our boring, all the critters are dead solution. If that's not the solution I want, then I'm looking for something where I can do B inverse times B times X is equal to B inverse times 0. But again, this just tells me X equals 0. So my interesting solutions happen when B inverse does not exist. And the way to guarantee that B inverse does not exist is to force the determinant to be equal to 0. So if that's my matrix, and I want to find the eigenvalues and eigenvectors. So I know that to find the eigenvalues, that's kind of my starting point. So I'm going to find the eigenvalues by solving the determinant of A minus lambda I equal to 0. So the first thing that I need to do is build what the matrix A minus lambda I looks like. I'm going to do this in 2 steps, but after you've had some practice, you'll probably skip this first step. So I'm going to build the A minus lambda I part. So here's my A matrix for -2, -3, 9, minus lambda times the identity. And because this is a 2 by 2 matrix, I need the 2 by 2 identity. So 1's on my diagonal, 0's on the off diagonal. So here's my A and my I matrix. If you have a number times a matrix, you can just multiply that number in everywhere. So 4, -2, -3, 9, minus And when I multiply the lambdas in, lambda times 0 is still 0, but I do end up with lambdas on the diagonal. And when I do that subtraction, we subtract keeping everything in its same spot. So I have 4 minus lambda, -2 minus 0, -3 minus 0, and 9 minus lambda. And I would say after you've done a few of these, we tend to skip straight from the starting point to a matrix where you've subtracted lambda on the diagonal and you've left your off diagonals alone. So this matrix is A minus lambda I. That's my new matrix. Question.
Why did you remove the, oh, I see, you just took out the zeros.
Yeah, I subtracted the zeros. Didn't worry about it. I don't have to show the subtracting 0 part. Okay, so we've formed our A minus lambda I matrix. Now I need to set the determinant of that matrix equal to 0. So when I do the determinant of 4 minus lambda, -2, -3, 9 minus lambda, I get 4 minus lambda times 9 minus lambda minus -3 times -2. And I'm setting that whole thing equal to 0. And then I'm going to go turn the lights on in the room. But if you want to go ahead and boil that out. I think it's kind of dumb that wherever the sensor for the lights are, it doesn't trigger off of me. It must trigger somewhere in the room.
I think it's like in the back, or to the side, where the sensor is.
Yeah. I gotta go all the way to the side of the room. Anyway. I will say if your handwriting is such that lambda is not a letter that is distinguishable in your handwriting, just go ahead and put an X. Just do something that you're going to be able to read when you're writing it. I've been writing lambdas for a while, so I'm cool with lambda. This is now an algebra problem. We're going to multiply this out. It's going to be quadratic. It will either factor or you'll have to use the quadratic formula. Every single time. It will either factor or you'll have to use the quadratic formula. Now, if you really hate factoring, you can always, every single time, use the quadratic formula. And if it factored, your numbers will work out nice. For me, factoring is faster. Did you all get this multiplied out? Did I stall for enough time? No? Okay, I'm going to give you a second to distribute that out and then clean it up so that it's in a spot where we can either use quadratic formula or factor it. This multiplied out. I'll kind of catch up with where you are. So let's see. So 4 times 6. Check my arithmetic. If I make a mistake, catch it now because otherwise we'll just do garbage in a second. So 4 times 6. That's
9.
Thank you. Thank you. Okay, I got the right number though. 4 times 6 is 39. Okay, 4 times negative lambda. So that's -4 lambda, -9 lambda. Negative times the negative makes that plus lambda squared. That's a positive 6, but then I'm subtracting it. So that's -6. So I have a hard time factoring if the squared part is not at the front. Sorry, my hang up doesn't have to be yours. -4, -9. So that's -13 lambda. And then 36 minus 6 should be plus 30. So if I'm going to factor it, I'm looking for two numbers that multiply to be 30, add up to be -13. Since that's positive, they have to have the same sign. So they're going to both be negative. You don't have a lot of choices. 6 and 5, nope. 3 and 10. Okay. So I've got lambda minus 10, lambda minus 3. So I've got two eigenvalues, 10 and 3. What it means to be an eigenvector is when I do the matrix times the vector, I get the eigenvalue times the vector back as an answer. So my matrix was 4, -2, -3, 9. And here's where I'm going to ask you all, am I calling this vector xy or x1, x2? No one cares. X1, x2? Okay.
Did you ever?
Like this?
No.
Yeah?
Sure.
Okay. It doesn't really matter. I just need a placeholder of something in there. This is the more common version from the book, by the way, is to use x1, x2. My lambda, we're going to end up doing this twice because there's an eigenvector that goes with 10 and there's an eigenvector that goes with 3. So I'm going to do 10 first, only because it's the number on the left. So I'm going to have 10 times x1, x2. This is secretly just 2 equations with 2 unknowns. And if I multiply out on the left-hand side and I just do that matrix multiplication out, I end up with 4x1 minus 2x2 is equal to 10x1. My bottom row, when I multiply out, I'm going to have -3 times x1 plus 9 times x2 is equal to 10x2. If we have done everything correctly up to this point, these 2 equations, in almost every case, are secretly the same. Because eigenvectors are never unique. These 2 equations, I claim, are the same if we just manipulate them a little bit. So if I take that second equation and I put all my x2s on the right-hand side, oh, question, answer. On the right-hand side, because that's my eigenvalue that I plugged in for lambda. So I've got like 10 times x1, 10 times x2, if I did the multiplication over here. Okay, so the bottom equation, I'm gonna get all my x2s on the right-hand side. So that's gonna look like -3x1. If I subtract 9x2 from both sides, I've got 1x2. The top equation, I'm going to do the same thing. I'm going to put my x2s on the right-hand side and my x1s on the left-hand side. So I'm going to subtract 10x1 and get -6x1. And on the right-hand side, I'd have 2x2. And I claim these are basically the same equation. Because if I multiply the bottom one by 2 or divide the top one by 2, they're the same. And what this tells me is that every single eigenvector has this relationship between its like x component and y component. So generically, I can write an eigenvector. I'm going to do what the book does, which is to always choose to just let x1 be equal to 1 and then figure out what x2 has to be to make it work. So if I let x1 be equal to 1 and I think about plugging that in, then I've got -3 times 1 is equal to x2. So my x2 value has to be -3. But in fact, I could have chosen anything at all to plug in for x1. So sometimes we would write this vector as saying, choose a constant for x1, and then x2 would be -3 times that constant. Now I gotta ask, since I didn't watch lecture, which version did he do yesterday? Plug in a number? Cool. Okay, cool. That was my guess, because that's what the book does. This is the more general version that some instructors do. This is the book version. I end up somewhere in between because I don't like to think about fractional critters. So I always choose values so that these are whole numbers, because I don't like to deal with fractions if I can avoid it. We're not done with this problem yet, though, because we still need to find the other eigenvector. So I'm going to do the same thing, multiply this out. I expect to get the same equation on the top row and the bottom row. Let's see if we do. So I've got 4x1 minus 2x2 is equal to 3x1. And then my second row, I've got -3x1 plus 9x2 is equal to 3x2. Looking at the top row, I got all my x1s on the left. By subtracting 3x1 from both sides, I'd have x1 is equal to 2x2 by adding that over. If I do the same thing down here, I'm going to leave my x1s on the left. So I would have -3x1. And then if I subtract 9x2 from both sides, I'll have -6x2. And they match. So if I choose an eigenvector, if I let x1 be equal to 1, then x2 would have to be equal to 1/2. And that is definitely the choice the textbook would make. The choice I make is to look at this and say, this tells me that my relationship between the x1 and x2, which I'm going to choose to write as x is equal to 2y, that's the same as saying y is equal to 1/2 x. And if I were to sketch that line, the y is equal to 1/2 x line, then any point at all on that line is an eigenvector, or could be the terminus of an eigenvector. So I'm going to choose something that has whole numbers. So personally, I might choose my eigenvector to be 2, 1. Both of these are eigenvectors. Eigenvectors are never unique. The relationship gives me an entire line where any point on that eigenline represents an eigenvector. So I find my eigenvectors by going all the way back to the ax equals lambda x version of the equation. But someone pointed out in the chat, we can also do this from the version that has zeros already. Meaning I can also do this with the version that's been rearranged to say a minus lambda I times x is equal to 0. And if you want to go back to this, that works too. We'll still get exactly the same two equations with infinitely many solutions. So if I do it this way, And let's say that I start with a lambda equals 3. So that A minus lambda I matrix, the 4 minus lambda, -2, -3, 9 minus lambda times my x1, x2 vector is equal to 0. And when we think about that 0, we need to make that 0 the 0 vector if we're going to do it this way. So if I choose to let lambda equal to 3, then this matrix 4 minus 3 is 1. 9 minus 3 is 6. And then I'm times x1, x2, and that's going to be equal to 0, 0. And if I were to do it this way and then do the matrix multiplication, I'd have x1 minus 2x2 is equal to 0. And -3x1 minus 6x2 is equal to 0. These are the same two equations that we got the other version. Did I mess up? Something has gone wrong. I should have gotten the same two equations and I didn't, because that's a plus. Cool. Okay. Here's my A minus lambda I matrix. And if I take the determinant of that, I'm going to have minus. So I'm looking at 2 minus lambda times -2 minus lambda minus 1 times -3. I will say, kind of like when we're doing matrix multiplication or addition stuff, take your time with the arithmetic, because making a mistake with a minus sign or making a mistake with addition or subtraction, right? All of that can lead you to something that looks really gross when the eigenvalues were supposed to be nice numbers. So I'm just going to take my time and write out an extra step. I'm not going to try to do this in my head. So 2 times -2, that's -4. 2 times negative lambda minus 2 lambda. Negative lambda times -2, that's a plus 2 lambda. Negative lambda times negative lambda, positive lambda squared. Minus a minus will make that plus 3. So I think that all simplifies down to lambda squared minus 1, which means we factor as lambda minus 1, lambda plus 1. And those are my two eigenvalues. Questions about this before I move on to do eigenvectors? Would you all like to try to find the eigenvectors on your own? I saw some head nods, so I will let you give that a shot. And as a reminder, when I'm finding the eigenvectors, I'm going back to that A times my eigenvector needs to equal lambda times my eigenvector. So I'm going to go ahead and do this for -1. And I'm going to get 2x1 minus 3x2 is equal to -x1 for that top equation. And my bottom equation would look like x1 minus 2x2 is equal to -x2. So if I take that bottom equation and I just add 2x2 to both sides, I'm going to get x1 is equal to x2. Does that look like what you all got? And if I rearrange the top equation, I should be able to get to the same place. So in terms of a pairing, I know that if I plug in 1 for x1, it means x2 is also equal to 1. So this is going to give me the vector 1, 1. If I do it all over again, but instead of a -1 there, I have a +1, I don't really want to have to flip the page, so I'm just going to do it. My AX equals 1 times X equations should look identical to these, but this side will be positive. So I would have 2x1 minus 3x2 is equal to x1. X1 minus 2x2 is equal to x2. And if I take the bottom equation that says x1 is equal to 3x2. I should be able to get the same thing on the top equation. I could add the 3x2. I could subtract the x1 over. Question.
As in like, because you have 2x1 minus 3x2 and 2 minus x1. But for the last problem, you said so that x1 equals x2.
Yeah, I'm just kind of talking through that instead of actually writing it. If you've done everything correctly, these two equations are equivalent. So I'm doing it for one of the equations now, but I'm not bothering to do it for the second equation. I'm just checking in my head that they're the same. Because otherwise you're solving the same equation twice, which is totally fine to do, but it's not necessary because they should be identical. Yeah.
Can I do that in my problem? Can I get x1 is 3 x2?
Down here?
Yeah.
Absolutely. And eigenvectors are never unique. So this tells me that every point on the line y equals x is an eigenvector. 2, 2 is an eigenvector. 17, 17 is an eigenvector. -4, -4 is an eigenvector. The textbook always plugs in 1 for x1. And regardless of which of these two equations you do that to, if you plug in 1 for x1, you will get 1 for x2. And up here, if you plug in 1 for x1 in either equation, you should get 1 back for x2. But just for completeness, let's take a look at this top equation. And if I plug in 1 everywhere for x1, then I've got 2 times 1 minus 3x2 is equal to -1. So if I rearrange this, I get, sorry, I'm trying to squeeze it in here. I apologize. I get -3x2. And if I subtract 2 from both sides is equal to -3. So I get that x2 is equal to 1. It shouldn't matter which equation you plug it into. If you plug in 1 for x1, you'll get the same value for x2, no matter which of these two equations you plug it into. But your point of 3, 3 is also an eigenvector, and it would also be a correct answer, and it would also get you full credit. Yeah. I think just for the sake of like having a method that's going to work consistently for every problem, I like plugging in 1 for x1. Even if sometimes it means we get fractions. Looks like, and I'm going to stack them up here. So I've got x plus 2y is equal to 0. And 2x plus 5y is equal to 1. And although he didn't tell us that we should use matrices to do this, I'm going to use matrices to do this for practice. So I'm going to rewrite this as the matrix equation, stealing my coefficients, times the vector xy is equal to the vector 0, 1. So I've got ax equals b. And I'm going to find A inverse to solve for x. So the first thing that I need for A inverse is I need 1 over the determinant. So that's 5 minus 4. I'm going to swap my diagonals and change the sign on each of my off diagonals. Conveniently, our determinant is 1. So my A inverse is just 5, -2, -2, 1. So my X vector I'm going to get by taking A inverse times the vector 0, 1. If I do that multiplication out, looking at 5 times 0 plus -2 times 1, -2 times 0 plus 1 times 1, and I get -2, 1. Now I can always check that that's a solution. I've got 2 options for how to check. My old school version of how to check is that says x equals -2, y equals 1, and that should make both equations true. So if I plug in -2 for x and 1 for y, top equation is true. If I plug in -2 for x, 1 for y, bottom equation is also true. It's a solution.
Just plug it into the 2 equations.
Correct. Yep. You could also graph them and show that that's the intersection point, but I think that is far more difficult than just plugging the numbers in. Other homework questions anyone wants to go over? Yeah. From that same assignment? Sure. So for D, I'm going to do the same thing and set this up as a matrix equation. So I am looking at 5, 1, 25, 5, and I can already tell interesting things will happen. It's equal to 1, 0, 0. 0, 0. Yes. So when I go to find the determinant of this matrix, if that's my A and I go to find A inverse, then I would have 5 times 5 minus 25 times 1. So I know that it's not invertible. And if it's not invertible, then I know that I've either got parallel lines or the same line. So which is it? Do I have parallel lines or the same line? I do indeed have the same line. So if I have the same line, then in order to express all solutions to that equation, I can say all points on the line y equals -5x are solutions. By the way, I've been using the phrase not invertible, but singular is also a totally fine vocabulary word for that. They're interchangeable. Yeah. That's me rearranging the equation. You could have left it as 5x plus y equals 0.
Oh, is that the thing?
Yeah. Yeah.